Okay, now we discuss another concept, the one of restriction of a function. So let me write down a definition first. So start with a function defined from a subset of the real numbers a into the reals, and let b be a subset of a. The restriction of the function f to b is denoted by the following symbol. It's f with a straight line, sub b. And this is defined as the following function. So it's a function with domain b that goes into the reals, and such that the rule defining it is the same that defines f. So the f restricted to b at x is simply equal to f of x for x in b. So basically the difference is that this function has a new domain which is smaller than the original one. So let me give you an example to understand what we're talking about. So take this function 1 over x defined from the real numbers except 0. That's its natural domain, the biggest possible. But I can... Okay, let's plot the function here. Now let's look at some examples of restrictions. So let's look at the restriction to the set, the interval from 0 to infinity. This is going to be a new function, so now I'm going to denote it g to make you understand this is really a new function. And what kind of function is it? Well, from the definition, it's the function whose domain is 0 to infinity, and such that g of x is equal to 1 over x on its domain. If I look at the graph, you see how the graph is different than the graph of f, because basically g is only a portion of f. The graph of g is only a portion of the graph of f. So even though the rule that defines them is the same, the functions are different because their domains are different. Let me give you another example. I can take the restriction to the natural numbers. Okay, there is a subset of the reals minus 0. Then this is the function defined from the natural numbers to the reals, such that a of x is equal to 1 over x. If I look at the graph, you should recognize that even though I'm writing a of x equals 1 over x, this x is a natural number, so I might as well write a of n equals 1 over n, and this, in fact, is what we know to be a sequence. A sequence is none other than a function whose domain are the natural numbers. So this is the sequence 1 over n. You can see it as the restriction of the function 1 over x when you allow x to just be a natural number. And that's basically the idea of restriction. That's all there is to it. Now let me write down a theorem which should be clear. The limit of restrictions. So now we use this unified way of defining limits. So I can state a theorem that involves both real numbers, infinity or negative infinity, in just one line without having to discuss it 9 different times. So take alpha and lambda being the extended real numbers, so they could be an actual real numbers or infinity or negative infinity. And let f be a function from a to r. Suppose that alpha is in an accumulation point of a, where we understand this being an abuse of notation in the case that infinity or negative infinity are not real numbers. Okay, that's the notation that we have used. And take b, a subset of a, such that alpha is also an accumulation point of b. Then, if the limit of f of x as x approaches alpha is equal to lambda, then I have that also the limit of the restriction as x approaches alpha is equal to lambda. So this theorem says if you have a function that has a certain limit, if you take a restriction, that has the same limit. And clearly we need to require alpha to be in the accumulation points of beta, because otherwise we cannot look at this limit here. And I also have a proof for you. You can stop the video and try to prove it yourself. This is just about using the definition, and the definition of limit and the definition of restriction. And so here is the proof. So we assume that the limit of the function f of x is equal to lambda as x approaches alpha. What does it mean? This means that if you take an arbitrary epsilon, positive real number, there exists a delta epsilon greater than 0 such that, this is our new unified notation, f of x is in the interval centered at lambda with radius epsilon for all values of x that are in A, because that's the domain of f, and in the punctured interval centered at alpha with radius delta epsilon. Okay, so this is what I have, and I need to show that the same is true for the restriction. Well, that's basically done, because what do we have in particular? B is a subset of A. So here, if I know that this condition here holds for all x in the punctured interval and A, for sure it will hold for x in B and the punctured interval, because B is a subset of A. So we have that for every epsilon there is a delta epsilon such that f of x is in the interval centered at lambda with radius epsilon for all x in B intersection, right? Clearly this condition is stronger than this one, because here you have less points in order to verify this. But in particular, this is exactly the definition of limit of the restriction as x approaches alpha being equal to lambda, because the only difference, the rule for the function is the same, the only difference is in the domain, and the domain appears here in how many x's satisfy the condition. So this concludes the proof of the theorem. Okay, it should be obvious, right? If a condition is satisfied by f, which is a bigger in some sense function, it should also be defined. It should be true also for any of its restrictions. Okay, and then let's now specify some particular restrictions. So take a function from A to R. Now fix x naught to be a real number. In this case, I'm not looking at infinity or negative infinity for x naught. So if x naught is an accumulation point of the set given by the intersection of A and the interval x naught infinity, then we define the limit of f of x as x approaches x0 plus, or from the right, to be the limit as x approaches x naught of the restriction of f to this interval, A intersection x naught infinity. In particular, this means I'm only looking at x's that are greater than x naught. That's why the notation x approaches x naught plus. Similarly, if x naught is an accumulation point of the set given by the intersection between A and negative infinity x naught, then I will define the limit as x approaches x0 minus, or x approaches x0 from the left, to be the limit as x approaches x naught of the restriction of f, this time to the set A intersection negative infinity x naught. Again, this means you're just looking at values of x that are smaller than x naught. And that's the definition. Now let's do an example. So let's take the function that we considered before, 1 over x, and take x naught to be 0. So we can observe that if I look at the domain, okay, now my A is this r minus 0. This domain, if I intersect it with the interval that's to the right of 0, it simply becomes 0 infinity, because that's a subset. So in particular, 0 is an accumulation point of this interval. And similarly, if I look at the other interval, the intersection again is given by the interval itself. And again, 0 is an accumulation point of this. So it makes sense to consider the limit from the left and from the right as x approaches 0. As x approaches 0 from the left or from the right. So this is the restriction if I restrict f to 0 infinity. And this is if I restrict f to negative infinity 0. So if I want to compute the limit as x approaches 0 plus, I have to look at the limit of this blue function. This blue function is the restriction, so this limit, clearly, this is positive infinity because the function is just going up and up intuitively. Okay, and then similarly, if I look at the limit as x approaches x naught, 0 minus, by definition, this is the limit of this restriction, now the green function. So in this case, it's clear that this limit is negative infinity. So if now I'm going to prove one of these formulae, it's kind of obvious, but just so that we know. So if you want to try it yourself, you can pause the video now and try to prove these statements formally. So let's verify that the limit as x approaches 0 of this restriction is infinity. What do I need to verify? By definition, take an arbitrary positive number as large as I want. Choose delta m to be 1 over m. That's clearly a positive number. Then what do we have? For all x's that are, I have to look at the domain of the function, and in this case, by definition of restriction, the domain is the interval 0 infinity. And I have to intersect that with the punctured interval with radius delta m at 0. Clearly, this results in simply the interval from 0 to delta m. So for all x's that are in this, we clearly have that x is between 0 and delta m. That's the definition of the interval. But what does that imply? That implies that x is between 0 and 1 over m, because that's how we chose delta m. And by taking the reciprocal, which I can do because x is positive, I get that 1 over x is greater than m, but 1 over x is the restriction. So I prove that for any arbitrary m, I can find a delta m such that this happens, and that's by definition saying that the limit as x approaches 0 plus is the limit of this restriction, which is infinity. Similarly, you can do the one when x approaches 0 minus. Now, in that case, you will have x is negative, so when you take the reciprocal, you have to reverse the inequality and you get a negative. So you get 1 over x is less than negative m. Okay? And now, to finish off, just one theorem. So take a function from a to r. Take a real number x naught, that's an accumulation point for a, and let lambda be now an extended real number, so it can be a real number, or here I write plus or minus infinity. Then what we have is that the limit as x approaches x naught of f of x is equal to lambda if and only if both the limit from the left and from the right are equal to lambda. And I encourage you to prove this theorem on your own. It should be fairly simple. One direction actually we already proved, because if you know that the limit of the function is lambda, then you know that the limit of any restriction is also lambda, so it gives you one direction. You only have to prove the other way around. If the limit of these two particular restrictions are the same, then the original limit is also the same.